Okay, let's find the extrema of f of xy equals e to the negative xy on the region given by x squared plus 4y squared is less than or equal to 1. If you think about it, x squared plus 4y squared equals 1 is the boundary of this region, and that's an ellipse. So the only x and y values we're allowed to plug in to f of xy are either on the ellipse or on the interior of the ellipse. So let's look first at the interior. See if we can find any critical points on the interior. And, well, okay, let me just say that's given, the interior is given by the strict inequality, x squared plus 4y squared is less than 1. Okay, well, find the critical points in the usual way. Find the partial with respect to x. So the partial of this guy with respect to x is actually going to be negative y e to the negative xy. And the partial with respect to y is going to be negative x e to the negative xy. So the idea to find the critical points, you're going to set both of these equal to 0. You don't have to worry about where the partials are undefined. The exponential function is always defined. And so the product of an exponential function and a linear function will certainly be defined for any x and y values. Okay, so solving these equations, well, the only way to make the first equation equal to 0 is when y equals 0, because the exponential function is never 0. Likewise, the second equation is only going to equal 0 when x equals 0. So your first critical point, your only interior critical point, is given by 0, 0. So circle that. We'll come back to that. Now, let's look on the border. Let's look on the boundary. The boundary is given by the ellipse. X squared plus 4y squared equals 1. So on the boundary, the boundary is given by the constraint curve x squared plus 4y squared equals 1. In fact, we can think of the constraint curve as g of xy equals x squared plus 4y squared. So I'm going to go ahead and use the method of Lagrange multipliers to find the critical points on that boundary. And we know from the method of Lagrange multipliers that del f is equal to some scalar multiple of what I'm calling del g. So all I need to do is find del f. Well, okay, I know the partials of f, so del f is going to equal negative y e to the negative xy I plus negative, well, let's just make it minus, that'll be easier, minus x e to the negative xy j. That's the partial with respect to x times I plus the partial with respect to x times j. Okay, and then del g is going to be, okay, well, here's g. The partial with respect to x is 2x, so 2xi plus the partial with respect to y is 8y plus 8yj. And then lambda del g would be 2 lambda xi plus 8 lambda yj. So if del f equals lambda del g, then corresponding components are equal. So set the corresponding components equal. So negative y e to the negative xy should equal 2 lambda x, and negative x e to the negative xy should equal 8 lambda y. And then the constraint curve I'm going to write down again is x squared plus 4y squared equals 1. So the idea is to solve this system of equations to get our critical points on the boundary given by that ellipse. Okay, well, we've got, let's see, equation 1, equation 2, and equation 3. Okay, about the only thing I can think to do is maybe solve equation 1 for e to the negative xy, which is 2 lambda x divided by, well, negative y. If I divide both sides of equation 1 by negative y. And then my idea is to plug e to the negative xy in the form of 2 lambda x divided by negative y into the second equation, substitute it in. And then if I do that, from equation 2 I get negative x, went down too far, times, okay, I'm substituting in the 2 lambda x divided by negative y, or you could have the negative out in front. And then that's equal to 8 lambda y. Okay, so the negatives cancel. Divide both sides by 2, get 4 on the right side, and cancel out the lambdas. And you're left with x squared over y equals 4y, or x squared is equal to 4y squared. And so that's good news. You've reduced it you've reduced the system of equations into, just using the first 2 equations, into one equation involving both x and y. And then finally, you can plug in to the third equation. So I know x squared is equal to 4y squared, so I can replace x squared with 4y squared and get 8y squared. 4y squared plus 4y squared is 8y squared equals 1. Or y squared is equal to 1/8, or y is equal to 1 over root 8 or 1 over 2 root 2, with a plus or minus in front, of course. And that means, what does that mean? That means that, well, okay, if we plug in y squared equals 1/8 here, and for just y squared we get x squared is equal to 4/8, or x squared is equal to 1/2, which means x is going to equal plus or minus 1 over root 2. So we get critical values, or critical points. Well, I think there's going to be 4 of them, so one way to list them is like this. Plus or minus 1 over root 2 is going to correspond to, well, 1 divided by 2 root 2. So that's 2 of the points right there. And then plus or minus 1 over root 2 could correspond to negative 1 over 2 root 2. Okay, so there's all 4 critical points on the boundary. Now, the idea is to plug in the critical points into the original function, which is f of xy equals e to the negative xy. See which ones give the biggest values. Okay, well, it won't take you too long to figure out what they are. If you plug in to f, if you plug in plus or minus 1 over radical 2 for x, and then you got to make the signs alternate. Minus plus 1 over root 2 for y. So there's 2 points here. Plus 1 over root 2, comma, minus 1 over root 2, and minus 1 over root 2, comma, plus 1 over root 2. You plug in either one of those to the original function, e to the negative xy, and you're going to get your max, which will be e to the 1/4. And if you plug in plus or minus 1 over root 2, comma, plus or minus 1 over root 2, so the signs have to agree, you'll get e to the negative 4. Actually, e to the, well, negative 1/4, I should say. If you plug in 0, 0, you get 1. Remember, 0, 0 was our interior critical value. You get e to the 0, which is 1. Okay, so this guy will be the maximum. This guy will be the minimum. And 1 is in between the two, so it's nothing as far as we're concerned, because we're just looking for the extrema. One thing I should mention is that when I solved this system of equations, in equation 1 and equation 2, I divided by variables. I divided by to solve for e to the negative xy. So in this one, I divided both sides by negative y. In this one, I divided both sides by negative x. Why is it okay to do that? Why is it okay to assume that x and y aren't equal to 0? Well, it might not be obvious, so let me tell you. By assuming that y does equal 0. If y does equal 0, then the right-hand side of this equation zeroes out. And we end up with negative x e to the negative xy equals 0. But e to the negative xy is never equal to 0, so that would imply x equals 0. But that can't happen. That's a contradiction. Because if both x and y are equal to 0, then the third equation is not satisfied. So it can't happen. So dividing by negative y, dividing by negative x, it's okay.